Okay, in our last lesson, we talked about vertical asymptotes for rational functions, and today we're going to talk about horizontal asymptotes. And so I kind of waited further in the notes last time to talk about the formal definition for a vertical asymptote, but what we found out was it looks similar to this, was that as f of x or y approaches infinity or negative infinity, then x approached a number. Well, a horizontal asymptote is going to be one that runs left to right, and so everything is kind of reversed here. It's going to be a y equals equation, and in that, f of x is going to approach the number, and x is going to be the one approaching infinity or negative infinity. So here's that same function we looked at in the notes from before, but let's look at the table um, in a different way. So let's look at this table for x here. It looks like x is approaching infinity, right? We're making x's get larger and larger and larger. And as we do that, it looks like the y's are getting closer and closer and closer to 0. And in this one, we made our x's very large in the negative direction, so negative infinity. But it still looks like as x gets larger and larger in the negative direction, y is still approaching 0. So it fits our definition. X is approaching really big or small numbers, and y is approaching this number, in this case 0. So this graph also has a horizontal asymptote at 0. So I want to show you that graph from yesterday. This is the graph from yesterday's notes, and we talked about the vertical asymptote, but the one that we just discussed for horizontal also runs right through where those curves approach. So they approach this line going towards positive and negative infinity, but y is just getting closer to the x-axis or to 0. It just doesn't ever touch it. All right, so starting off with the formal definition on this one, you need to be able to identify a horizontal asymptote from a chart. And then we're also going to talk about how we can identify horizontal asymptotes from an equation. And so to do that, we're going to do a little bit of mathematics, and then we're going to give you a little bit of a shortcut. But we know that we want to know, as far as horizontal asymptotes go, what happens to y, when x gets really, really large or really, really small, or a big number in the negative direction. So this one's easy for us to think about, just x getting very large. So I'm going to use this when I talk about this next part of our notes. But when we look at this in behavior, the question is, what is happening to y as x gets very large or small in the negative direction? And so in order to get the answer, we are going to rewrite our equations. We're going to rewrite these equations and divide by the highest power of x that we see. Everything in here. So here, our highest power of x is x to the second. So this is what we're doing. We're going to divide 4 by x squared. We're going to divide x squared by x squared and 1 by x squared. And then if we can, we'll reduce. The 4 over x squared doesn't reduce. The x squared over x squared is just 1. The 1 over x squared does not reduce. But now we're going to go back and consider the question. The question is, what happens if I put a really big number in here for x and then square it? So if I were to put 100 in there and square it, 100 times 100, that's a pretty big number. And 4 divided by that is a very small decimal number. If I put 1,000 or 10,000 or a million in here and then square it, then 4 divided by that is going to be a very tiny, tiny number. It's actually getting smaller and smaller and smaller. It's approaching 0. When I put in a big number here, this value approaches 0. 1 is just 1. But this also would approach 0, or I get 0 divided by 1. and 0 divided by 1 is 0. And it turns out that this idea here, because we're putting big values in for x, we're seeing that y is getting close to 0, or there's a horizontal asymptote at y equals 0. All right. So we're going to do that with each of these examples. So in this one, the highest power here is just x, so we're dividing everything here by x. So the x is reduced, and I get 2 plus 1 over x. Here, the x is reduced to just 1 plus 1 over x. And again, the idea is that I'm going to put a very, very large value in here for x. And the bigger it gets, the smaller this overall number gets, or closer and closer to 0. So I get 2 plus 0 over 1 plus 0, or just 2 over 1, which gives me 2. So in this example, I'm going to have a horizontal asymptote at y equals 2. Okay, so we have one more of those where we're going to work it out like that. So highest power of x here is x squared, so we're going to have x squared over x squared minus 9 over x squared, x over x squared plus 2 over x squared. So that reduces to 1 minus 9 over x squared, and this would reduce to 1 over x plus 2 over x squared. And again, as I put in a very, very large number here for x, all three of these fractions are going to approach 0. So I get 1 minus 0 over 0 plus 0, or just 1 divided by 0. Well, you can't divide by 0. That is undefined. And since you can't do that, then there will not be a horizontal asymptote in that instance, because this is not possible. You can't do that. You can't divide by 0. All right. So, we could leave it at that, and every time you see one of these equations, you just divide through by the highest power of x, and then we can solve and get our horizontal asymptotes. But there is a little bit shorter way, so I'm going to show you the shortcut now. I just wanted you to know where the shortcuts come from. This is actually called limits. It's a limit process that you'll learn more about in calculus. But here's where the shortcut comes in. So this looks pretty complicated here, but it's really not. All it's saying is that this represents my highest exponent in the numerator and the denominator. In the numerator, this is n, highest exponent, n, highest exponent. And these represent the coefficients in front of those highest exponents. And that's the most important part. And usually when we write a polynomial, if this is cubed, the next would be squared, and then we just reduce down from there. So this question actually has to do with what we did in our notes from the day before. It says the graph has vertical asymptotes at the zeros of the denominator, right? We set the denominator equal to 0. So at the zeros of q of x. The next three questions have to do with what we are doing today. So, okay. This is talking about horizontal asymptotes. And if you'll look, they're referring to n and m, these exponents here. So we're going to refer back to examples 1, 2, and 3 and compare our exponents. So looking back at the 3 examples that we did, in which of these does it look like the highest exponent in the top was smaller than the highest exponent in the bottom? So here it looks like the exponent in the top is bigger than the one in the bottom. Oh, you can't see what I'm doing. This one is larger than this one. So we're not talking about this kind of situation. So let's look back on the other side. On this one, the exponents were the same. They were both to the first power, but here, there's not even an exponent on the top, but the denominator is larger exponentially than the top. So we're talking about this situation, and in this situation, our horizontal asymptote ended up being y equals 0. So what we're saying here in general is that no matter what the polynomials are, if the exponent on the top is smaller than the bottom, then y equals 0 is always going to be the horizontal asymptote. If the exponents are the same, so in our examples, looking at the one that's the same, it wouldn't be this one. That would be this one, where the exponents were the same, both x to the first power. Our horizontal asymptote ended up being 2. Well, where did the 2 come from? This comes from the coefficients in front of those terms. So the coefficients of x to the first, 2 over 1 gives me 2. So in this one, if n equals m, then the line y equals the coefficient in front over the coefficient in front, or in this case, a to the n over b to the m. Just use the coefficients. And that will be your horizontal asymptote. And then lastly, if the exponent on the top is larger than the exponent on the bottom, that would be the one that's at the top of our page, we got that there wasn't a horizontal asymptote. So in this instant, there is no horizontal asymptote. So really, in short, all you have to do is look at the exponents to determine your horizontal asymptotes. If the top exponent is smaller, it's 0. If they're the same, you use the coefficients. And if it's larger, then there's not going to be one. So let's use those 3 rules and see if we can do these 3 problems. Let me see if I can get all this in here at the same time. Maybe. There we go. All right. So in this one, it looks like our coefficients are both, our exponents are both 1, or x to the first power. And so therefore, we're using rule B. And we just use the coefficients in front, 2 over 1. So our horizontal asymptote is y equals 2. Now, I don't want you to think it's always 2. So let me give you another example. If we had I'll put it down here. If we'd have had f of x equals 3x squared minus 4 over 2x squared minus 5, the highest exponent is still the same, and we would use the coefficients in front for our horizontal asymptote, and our horizontal asymptote would be y equals 3 over 2. Okay? All right. So next, we have one where there is no exponent in the top. There is an exponent of 2 in the bottom, so the top is smaller than the bottom. That would be rule A. And so therefore, our horizontal asymptote is y equals 0. And then for this last example, the exponent on the top is larger than the one on the bottom, which is understood to have an exponent of 1. And when the top is larger than the bottom, there is no horizontal asymptote. All right, so this one was rule C. All right. Now, for our vertical asymptotes, this is a review from yesterday's lesson. So vertical asymptotes come from the denominators. So we want to set these denominators equal to 0. So for number 7, we'd have x plus 1 equals 0. So x equals negative 1 would be our vertical asymptote. For number 8, x squared plus 1 equals 0. X squared equals negative 1. You cannot take the square root of a negative number, so there will not be a vertical asymptote. And on the last one, we set x minus 2 equal to 0. X equals 2 would be our vertical asymptote. So for vertical asymptotes, remember from yesterday, we want to set the denominator equal to 0 and solve. For horizontal asymptotes, we're just going to look at the coefficients. We need to know rules A, B, and C to use our shortcut for horizontal asymptotes.